Hey there, in this video, we're going to look at differentiable functions, but from a graphing perspective. And we'll start by remembering what it means to be differentiable. And we'll also look at the limit definition of a derivative because we may need that as well. Let's go. So first thing is, let's recall a couple things. The first one is, what does it mean for a function f to be differentiable? So f is differentiable at the x value of a if f prime of a, the derivative at a, exists. Okay, so what does that mean? What does f prime of a exist mean? Well, f prime of a, by definition, is a limit, and it's the limit as h approaches 0 of the secant line slope. So it's the y value, or the output at a plus h, minus the output of the function at a, divided by the change in x, a, which is a plus h minus a, which just simplifies to h. So when we take the limit, this is a two-sided limit, don't forget. When we take the two-sided limit of this function, if we get a finite value, then this limit exists, therefore the function is differentiable at a. Okay, and remember what this represents. This is a limit of the secant line slope, which turns into a tangent line slope. So lots of ways to look at this. F is differentiable at x equals a if the tangent line slope exists. Okay, so let's look at some examples here of some graphs. Determine where each function is not differentiable. Determine where each function is not differentiable. And I've got a graph here prepared already. So this is an interesting graph. Let's analyze the derivative at various values. Like at x equals 2, what would the derivative represent? Well, it would be the slope of the tangent line right here, which is some finite value. So f prime of 2, so this graph is y equals f of x. Let me write that in red since the graph is in red. The graph is y equals f of x. We can say that f prime of 2 exists. It's some positive slope, some finite number. And, at 1, we get some finite positive slope as well. At -1, we get the same slope, it looks like, at -2. And I'm looking at integer inputs, but you can also look at fractional inputs, like right here, you get a positive finite slope. Down here, you get a positive finite slope. But then look at what happens as you get infinitely close to 0. As you get infinitely close to 0, your tangent line turns completely vertical. Now, what does that mean? So your tangent slope here is your rise is some number. It could be positive or negative, by the way, depending on if you measure up bottom to top or top to bottom. But the key part here is the run, the horizontal change. The delta x is 0. So here the tangent slope does not exist. That means f prime of 0 does not exist because the tangent slope does not exist. You get a vertical slope. And if the function has a derivative that does not exist at 0, then that means f is not differentiable. F is not differentiable at 0. And we can see here that it's differentiable everywhere else, but just not at 0. So vertical tangent slope results in a function not being differentiable. Let's look at another case. Let's say we have a graph. This time I'll hand draw some graph. This time our function y equals f of x does this kind of thing and has sort of a sharp corner here. So this is y equals f of x. And again, we can start to look at various slopes. we get finite positive slopes. On this side, we get finite negative slopes. And I want to analyze what happens right here. Let's say that this is at the x value of 3, okay? As we get infinitely close, our tangent slopes on the right side are positive, but our tangent slopes on the left side are negative. So that two-sided limit we were talking about before, as h approaches 0 from the negative side or the positive side of 3, we get different slopes from the left and right side. So f prime of 3 does not exist because the tangent slope does not exist there from both sides. They don't equal the same value. Let's say that the tangent slopes do not approach the same value, from both sides of 3. So f is not differentiable at 3. Now, I called this a sharp corner, but it actually has a name. It's called a cusp, C-U-S-P. A sharp corner like this is called a cusp, where you have an instantaneous change in behavior to your function. Your function is not differentiable there. Notice in both of these cases, the functions are continuous. So at 3, the function is continuous. There's no break or gap at 3. In example 1, at 0, the function was continuous. There's no breaks or gaps at 0. Example 3, let's see what happens if we do have a break or a gap. Let's say our function, looks something like this. This is, let's say, y equals f of x again. And the problem here is in the definition of the derivative. Our a value, let's say right here, we'll call this, we'll say this is 1 on the x-axis. What happens at 1? We can see that, every other place except for 1, we're certainly going to have differentiability. You're going to get a tangent slope. But what happens at 1? Well, the limit definition is dependent on your a value. You're always going to base it on your a value, the output at a. In this case, a is 1. So the function here, the output of 1, happens at this closed circle right here. So when you start considering secant line slopes from the left, you pick points over here, and then you got it, if you pick f of a plus h, that would be this point, and then f of a would be right here. Your secant line slope looks like that. And as you get closer and closer, you get secant line slopes that do this. Well, those are not going to approach the same slope from the other side as you get infinitely close to a. From the other side, if you pick this point and this point, your secant line slope looks like that. So your slopes from both sides of 1 do not match again. And that's always going to happen if you have a discontinuity. If you have a discontinuity at a point, then the derivative does not exist. So f prime of 1 does not exist. A couple reasons. The simplest is f is not continuous at 1. And there's a theorem that says if a function is not continuous, there's no way it can be differentiable. So we could just cite that. But we could also analyze the secant slopes as we just did. So f prime of 1 does not exist. F is not continuous at 1. Therefore, f is not differentiable at 1 either. So now we've seen 3 cases of analyzing graphs and where they're differentiable based on the definition of the derivative, which is the tangent slope, which is based on a two-sided limit. All right, I hope that makes sense, and good luck working problems with differentiability.